Swayam Prabha. Digital India. Educated India.
So in this lecture we are going to derive two expressions. One, what is the effect of temperature on the solubility? You know that solubility of two phases into another, it depends on the chemical potential equality of a particular component. But one needs to derive a mathematical expression to find out whether we can actually calculate the solubility as a function of temperature. So how to do that? To do that, let us assume a simple phase diagram, okay, which has a terminal solution on the one side, and other side there is very little solution. Okay, and on this side we assume there is very little solubility. So, and you know these two curves, one here, one there, they indicate how the solubility of A in B or B in A changes as a function of temperature. The question is this: can I have a mathematical expression using thermodynamics of solubility as a function of temperature? So let us consider an alloy composition, this, which is solidified, and then its solubility limits will slowly change. As you see, beta is basically having very low solubility of A in B, but alpha is large, correct? So because of that, because of this, they are going to, you have to see how this phi and decomposition diagrams will look like. So I am going to draw the phi and decomposition diagram there. And because beta has a very low solubility, so beta phi and decomposition diagram will look like this. Okay, it is better to use a color chalk. That's what we have been doing. And the common tangent between them has to be drawn a little bit this side, otherwise the phase diagram data will not match, is it not? Because this is where the phase diagram . Okay. Now I draw a common tangent . So that's what is your equilibrium composition. Now as you see here, two things you must see carefully. Let me explain. One is that this line tells you equilibrium between the chemical potential. Because this is A and this is B end, so here also it will be A. We can extend this line till further, wherever it meets there. So that means it tells you that we have a small solubility in beta and large solubility in alpha and B components, and we are going to do that. So as you know, mu is given by this expression, okay, G let me see whether I have written it properly or not. Sometimes I also do mistakes. Did I write it properly? No. Something is missing here, that's the gamma. We have seen that, right? So if I write down this will be in the alpha phase. Fine. So that's basically the chemical potential of B in alpha, that's equal to the phi energy G plus 1 minus xp whole square into sigma. Sigma is your, gamma, not sigma. Gamma is your interaction parameters and plus RTL and xp. I have already given you this expression. Now we can write down this expression like this, minus 1 minus xp whole square this is equal to mu B, and this may be GB, that is actually GB alpha. Okay, GB alpha means the alpha G, the value of phi energy of alpha phase when at the B end, okay. So that's nothing but this difference mu B alpha, you can see here GB alpha is somewhere there, meeting there, okay. So that's the difference between these two, that's what is called delta G. So I can write down again, that is the difference of phi energy of the alpha phase when it is in equilibrium with beta minus when it is not in equilibrium with beta, okay, whenever it is present. So if I extend this phi energy curve, this is what is going to meet here, and that tells you the phi energy of the alpha when your pure B is at the pure B end. Delta G, okay, that's the difference of delta G. So we can write down then very nicely the expression. So that's actually, so therefore at xb equal to xbe, that is at this composition, this can be written 1 minus xbe whole square minus RT ln xbe. Okay, so then what I can do? I can write down xp, oh sorry, I have been missing this term always. xpe is nothing but exponential minus delta G plus this divided by RT it goes there, xp equal to xp. So that's actually solubility limit of that's the solubility of xp as a function of temperature. So you must have a knowledge of the interaction parameter gamma and the phi energy change between G alpha and this equilibrium between alpha and beta, then only you can calculate that. And this can be further modified much simpler, because once you know that delta G is depends on delta H minus T delta S, you can little bit modify it, but that doesn't matter. This is what is the expression for the solubility as a function of temperature for alpha phase. So only one parameter you need to know, because the interaction parameter is always known for the two components A and B. What you need to know is the delta G. So that can be only obtained if I know the phi energy functionals. Basically it's the phi energy. What is delta G? Delta G is nothing but phi energy of alpha phase at the period B end. So that can be easily obtained if I know the free energy expression of the alpha phase minus the chemical potential of B in alpha. So that chemical potential can be obtained when you draw a common tangent. But this one can be obtained when you know the G alpha. G alpha will be a function of xb. Okay. Obviously, G alpha is a function of xb, temperature and pressure. So we assume pressure to be constant, then G alpha is a function of xb and the temperature. So then this is obviously to be obtained first. Once you know these functions, then only we can calculate at period B end what is the G alpha. That means by putting xp equal to 1, xp equal to 1 you will get Gb alpha. And in that case Gb alpha as xp equal to 1 will be only a function of temperature, because we have assumed that xp is a constant here. So that is what I am saying. So once you know this parameter by the way you have derived, and you know the interaction parameter gamma, then actually we can easily calculate what is the effect of temperature on the solubility of B in alpha phase. So that is the first thing you should know. This is important in many of the calculation using your nucleation kinetics. So now let us, whatever time I have in this lecture, let us derive another important expression. You know, interfaces will have a strong effect on the phase transformations. Interfaces means between two phases. Suppose you have one solid, one liquid phase, or one solid and another solid, interfaces will develop, and these interfaces will have a strong effect on the phase transformation. So how do I do that? So that means what we are going to do is, as is written in this book, the influence of interface on the equilibrium. So let us suppose, so therefore influence, remember we will discuss interfaces in detailed manner, that is what we are starting off now, interfaces. Basic idea is that whatever derivations I have done so far for the free energy, we will assume that interfaces has no effect basically on the equilibrium. Why? Because we assume the interfaces to be very small in number, or small actually in, to affect the equilibrium. But that is not the case. Why? Because let us assume I have alpha phase, and in which small amount of beta phases are forming. These are all beta phases, correct? So what is the effect of interface between alpha and beta, this interface, on the equilibrium? If we assume that the beta is very large in the sense is that the surface area, interface area between beta and alpha is very large, then there is a strong effect on the equilibrium. So that must be brought in. How we can do that? It is very simple case like a soap bubble in a soap solution. We know that if I have a soap bubble in a solution, the pressure increase. Pressure inside the soap bubble is nothing but this. This is gamma. Okay, and this is the radius of the bubble. So similar analysis we can apply here. How we can do that? We can always assume that both alpha and beta phases are subjected to atmospheric pressure P. But because beta is small and within alpha, just like a soap bubble in a bucket of soap or mixture, water mixture, so therefore there is extra pressure within the beta phase, just like a soap bubble. In a soap bubble we always assume extra pressure. So because of this, because the beta phase is well inside the alpha and very small in size, there is an extra pressure on the beta phase because of that aspects, and that is exactly same as what happens in a soap bubble and this extra pressure is nothing but 2 into gamma divided by r. So we can write down this extra pressure here, in this case is 2 gamma alpha beta divided by radius of the beta. If this is twice r, then we can write an r is the radius of the beta phase particle, average radius. So what we need to know is the interfacial energy between alpha and beta. That is the effect. Now how does it affect the free energy? As you know, free energy has a pressure temperature term, right, pressure volume term, and the way it affects is like this. Change of free energy will be equal to change of pressure multiplied by volume, okay, multiplied by the basically molar volume. And that's obvious. G is nothing but E plus PV minus Ts. So pressure, effect of pressure, because of change of pressure, if everything else is constant, temperature and other things are constant, the change of free energy because of pressure change will be equal to this, okay, because we assume volume is not changing much. So therefore we can write down delta G is nothing but twice gamma alpha beta multiplied by Vm divided by R. So that is the change of free energy because of the interface. Because you have a finite interface between alpha and beta, this is what is the effect which will happen. This equation you have seen many times, but probably have never thought how it is to be derived. This derivation of delta P equal to twice gamma by R is available even in 12 standard books. So there is no point in doing it. The pressure difference can be easily calculated. From this expression we can easily get down into G equal to twice gamma alpha beta multiplied molar volume of the beta phase divided by the radius of the beta phase. So smaller is the R value, higher is the delta G change. Smaller, say larger is the alpha beta interfacial energy, higher is the delta G. So that means what? This change in free energy because of the pressure, because of this interface basically, is directly proportional to the interfacial energy, inversely proportional to the radius of the particle. That's why smaller the particle, that's why the precipitates, actually we will see the precipitation case, they are nano size. So therefore effect of the interfacial energy on the free energy will be more. So now we understand whatever calculation of free energy and derivations we have done so far has to be corrected with this effect, which we have not done so far, because I was only talking about the cases where interface was very, the negligible effect. In fact, in bulk thermodynamics, you always ignore the effect of interfaces, dislocation, defects, all we ignore, because that helps us making the things understandable, easily handleable. Now that you know how to add it, so for every G expression means every G free energy expression which you have derived, in order to take in the consideration effect of the interfaces, we have to add this term. What will happen if we add this term? Graphically let us see what will happen. What will happen is basically the compositions which are equilibrium composition of the interface will change. So let me draw it here. I just draw a free energy composition diagram for two phases, alpha and beta. In one case, the R is infinity. So if R is infinity, then delta G change is 0, because 1 by infinity is 0. Other case, R is finite, that means R is having a specific value. So this is my suppose alpha free energy curve. Okay. Now I am going to draw two free energy curves of beta, one for which this is G beta. Okay, let us write down properly. This is G beta, R is equal to infinity. Okay, that means very large value of R. Very large value of R means what? These interfaces are basically do not have any effect onto that. Remember, this is delta G is inversely proportional to R. The smaller the R, larger is the effect on G, delta G. Now if I have a finite value of, so therefore, yes, what is this equilibrium? To equilibrium we need to draw a common tangent. And you see this is what is the xp alpha when r is equal to infinity, and this is xp beta when r is equal to infinity. Okay. Now, so therefore, if I now consider when r is not infinity, r is having a definite value, that means this term has to be added to the free energy curve. This is the free energy curve. So, if I add, this will go up. This is addition, so therefore it will go up. So, let me just draw it. So, this is G beta when r is equal to r, some finite value of r. So, now if you clearly see the common tangent, common tangent of, we have to change color of the systems every time. So, then the equilibrium between alpha and beta phase gets shifted. This is the composition xp alpha at r is equal to r. So, the equilibrium composition between alpha and beta gets shifted to the higher value. That is the effect of change in because of the influence of the interface. So, if I have a finite diameter of the particles or the phases of beta in alpha, the equilibrium compositions will shift. So, therefore, effect is always observed in change in equilibrium concentration. So, the phase diagram boundaries whatever drawn, they are drawn actually at a when r is equal to infinity. So, for r equal to any other finite value, we have to redraw the phase diagrams. Actually, you have to calculate it everything. To calculate, you need gamma alpha beta, and this gamma alpha beta is very rarely measured normally. So, that is why the problem is. Atomic volume can be obtained very easily. So, these diagrams actually now drawn for different nano sized particles. Suppose if r become 100 nanometers or r become 50 nanometers, we can actually draw these diagrams separately on the same phase diagrams or on separate also possible. Because composition is changing, and this is suppose a temperature T equal to T1. So, similarly for other temperature also this effect will be visible. Okay. Now, one can actually, we have assumed that particles to be spherical, but it may not be the case. If it is non-spherical particle, this can be also derived and can be shown. The same formula actually applies. There is no problem. We can always assume we can always assume the radius of a non-spherical particles as a equilibrium. We can equate that the surface areas of a sphere and the surface area of the non-spherical particles and find out what is the similar r values, and we can do the calculations. It is possible. It is there in the book, or you can also actually do as a part of a homework. That is not a big problem. We can do that. Otherwise, I can explain you later. So, in a nutshell, with all these descriptions, we have completed the discussions about the thermodynamics of the solutions, thermodynamics of the order phase, intermetallics, effect of pressure, temperature, even interfaces. We have started that also. So, the next class we are going to start discussion about the diffusion. Okay, diffusion will have and diffusion actually controls many of the nucleation and other dynamics of the phase diagrams, after the phase transformations. So, we are going to discuss about that, and then after diffusion we will discuss detail about the interfaces, what kind of interfaces will be there and how they are going to affect, because this value of alpha beta interfacial energy will depend upon type of interface, and that type of interface has to be then discussed. Then we will start different types of phase diagrams.